Okay, let's get started. Good morning, everybody. Doing well. Welcome to another Builder Forum series, our last of the year. Quite a busy year for our Builder Forum series. Thank you for joining us once again. So today's lecture, our workshop is rather unique. It's a bit special. Today we're focusing on our part 3 peers across the province. We generally really focus our efforts for our part 9 builders, but today we felt, or for this session, we felt we really want to talk to our part 3 developers, builders, and professionals and trades folks and everyone else on a pretty important topic, a complex topic that we don't really talk about enough, and we want to share some information with you to help you succeed. So today's workshop is on air leakage and part 3 compliance from the Building Energy Department. We present JRS Engineering, and that's Jack, Zekin, and Andrew, our air tightness specialists, who are going to give us a lot of information on really how to make sure that you guys can knock it out of the park and be compliant at final. Today's workshop is brought to you by us. That's Kira Lai, our technical assistant, Jean Surendran, our building energy specialist, and especially for this group of people, I'm sure all of you know him, or most of you know him through your BP applications. And then there's myself, Kevin, the manager of building energy. I'd like to thank our supporters, our partners, AABC, BC Housing, OABC, and more for fully accrediting our workshops, for putting their trust in our education materials, and by your attendance. You will get a certificate at the end of the day, and you can use that to get your CPDs for your respective bodies. And also note, with your certificate, you can submit that to EGBC for potential credits. Okay, so on today's menu, it's air leakage and part 3 compliance. So the Township of Langley is going to start with a briefing. We're not going into detail, but a briefing. The brand new overheating protection compliance requirement 933.3.1 bracket 2 for part 3 buildings. Now, while this is clearly part of part 9, this does apply to part 3. Part 3 application compliance methodologies are can be rather broad. We will touch on it today for part 3 type C buildings, and then we're going to get to the meat of the day with Jack, Zekin, and Andrew, air leakage and BC compliance. I want to highlight, and a lot of you are using the chat. Please use the chat for questions later. Either JRS Engineering will kind of select some questions during the workshop if they feel it's important to answer that right away, or they will compile all of the questions from the chat and answer them in order at the end with Kira facilitating. And as a practice, or if you haven't already, please use the chat and tell us, hey, where you're watching from. Also, today's it's a bittersweet day. Today marks nearly the end of Kira Lai's 8-month co-op term with us. Kira came from SFU. She's in the late stages of her education. She joined us from a co-op term for the last 8 months. She's helped us tremendously with a lot of our key priorities, including one of our major priorities, which is delivering education to our builder communities. She's been a humongous help, and a lot of the work she's done was really to support y'all folk. So please join me in wishing her farewell and the best of luck in her studies and eventually to the workforce. So please, thank you all for giving her a bit of a clap. So thanks for that. Thanks, Kira. Okay, so let's get right into it. We'll do a bit of a recap of our last lecture. If you had attended it, great. If you haven't, you might wanna watch it. If you do work on part 9 buildings, or even there is some applicability to part 3 buildings, And that was airtightness and step code for Part 9 compliance. We did a talk on overheating protection, an in detail talk for Part 9 compliance for our overheating protection brand new bulletin. It gives you the 3 fully defined compliance pathways for the brand new Part 9 overheating protection requirements. Kiris walked us through a little bit more about our new product, Green Buildings on Demand, where you can watch pre-recorded workshops online whenever you want and still be fully accredited and get your CPDs. It's likely the only thing of its kind that's free in British Columbia, if not Canada, where you can watch our buildings related workshops and get a continuing professional development credit. Then James Higgins and James Bourget from RDH, a very well-respected building envelope consultancy, told us all about how to be compliant at the Part 9 level with tips, tricks from a theoretical view, walking us through different transitions, lots of great 3D mock-ups, where the meat of, however, the workshop was actually, for the first time, a live streamed kind of in-person online workshop where James Bourget took you to his mock-up lab on airtightness to show you real mock-ups, real applications of what you can actually do. These are not 3D images. These are not slides. This is him working on mock-ups to show you what you can do. And there you can see there's a gasket for some piping and showing you exactly how you can use that to improve your airtightness and meet the requirements as we go from step 3 and beyond. Check us out. It's a bit hard to see. It's tol.ca, /gblearn. Buildings Learn. For more information on how you can access our free learning hub. Okay, so let's get right into it. So as noted and premised, we're going to talk about overheating protection for Part 3 buildings, but it's going to be a briefing. If you have more complex questions, you can put them in the chat and you can email us. So if you're looking for our bulletin, is geared for Part 9, but it can be basically applied to Part 3. Visit our website, look for bulletins. You can go to the Building and Development tab at the top. On the right hand of the screen, and look for bulletins, forms, and resources. Click around and you'll find our PLI bulletin on overheating protection. Okay. So overheating protection is 933.3.1 bracket 2, and we're talking about the Part 3 application. So first, this is important. If you didn't know, inform you that overheating protection is a BC requirement. This is, as of the new BC 2024, is meant to mitigate the impacts of heat events and climate change. This stems from the 2021 heat dome event, where, as you all recall, it was a very hot 7 to 10 days. There were hundreds of people who suffered fatality from that. I think the overheating protection requirement is meant to mitigate overheating, but as well, as we acknowledge, step code or high performance homes and from our learnings from passive house homes. You put lots of insulation on a home. That's wonderful for winter. It keeps the heat in, but in summer, it also keeps the heat in. So we want to acknowledge that as we get higher performance and lower emission buildings, we need to understand how our buildings are changing and evolving. And with the heat dome event, it kind of gave us a bit of a shake. And so we really need to address some of the more risky outcomes of having heavily insulated buildings. Now, I will highlight, before we get into some of these really kind of surface level examination of compliance, Part 3 compliance, and really this is for Type C buildings. This is for condos, apartments. Part 3 compliance can be simple. There is a simple way, simple ways. One end of the spectrum. All the way on the other end of the spectrum, you can be very creative and you can be very innovative. And we suspect we're going to see those methodologies, and that's wonderful. If you have time and resources and you really want to kind of see how you can meet the requirement, in new and modern ways, go for it. If you're looking for simplicity and predictability, yes, there's methodologies for that as well. And this is really important. Item 3, part 2, underlined. Currently, as of today, and this is, I'm talking to modelers, particularly, and mechanical engineers and kind of and beyond, but particularly this is important to acknowledge. Well, 933.3.1 bracket 2 applies. It's new and it applies. Step code for Part 3 Type C buildings is required across BC as of May last year. All Type C Part 3 buildings are required to meet Step 2 for Part 3 buildings. And with that, since 2018, Step Code has, through City of Vancouver energy modeling guidelines, overheating limits. Okay, your modelers are 100% fully aware of this. Mechanical engineers are probably aware of this as well, and architects. Both requirements are applicable at the same time. I'm just going to put that there and let you chew on that, and you know, you can ask your modelers, you know, how that might affect you, because it can affect you. On the right in the box there is the snippet from the code. The long and short of this is, and again, we're not going to go into detail compared to the workshop we had last time. If you want to go into detail, watch the workshop on our Learning Hub. The requirement effectively is there needs to be at least one space inside a dwelling unit. Okay, one space, could be a bedroom, be a living room. One space that you must demonstrate that will not exceed 26 degrees at summer design temperature. That's it. So let's get into the bulletin. The bulletin is meant to provide some guidance. For Part 9, it's quite clear. The same guidance really can apply to Part 3 buildings. So as notes, it applies to all Type C residential buildings. So there's some notes there. Please do read those. That's going to help you, kind of premise you to go through the compliance methodologies. This is important. In the notes and in the BSSB bulletin, your mechanical solutions must be permanent. Means is you cannot go to, you know, your kind of local vendor and get a whole bunch of window shakers and kind of put them in the window. That's not a permanent solution. Or rolling, your rolling, 10,000 BTU AC is ducted through a hole in the wall or some kind of space in your patio door. That's not permanent. It needs to be a permanent solution. And as always, and for any scenario whatsoever, this is a reminder, however, your documentation and methodologies are at BP, building and permit. If there's any changes throughout the design process or construction process, that triggers a new reporting of how you will meet this requirement. That's generally, across the board. It's just a reminder. Okay, this bulletin goes over 3 methodologies. Generally, it can be similar compliance, but we do acknowledge that we can see some innovative, very creative methods that are really more only suited for Part 3 buildings. So the first compliance method for both Part 9 and Part 3 Type C units, remember, your minimum requirement is showing that at least one space is cooled to 26 or better. The easiest way, or one easy way, and we see this a lot of the time in Part 9 buildings, when you have central cooling or cooling that serves the entire conditioned space of the dwelling unit, when that is the case, or otherwise called central AC, through a heat pump or air conditioner, you are compliant. The next compliance methodology is localized cooling. And this is what we also call a space, or cooling one space in the dwelling unit. This is being kind of colloquially called a refuge room. And that's the idea that during a heat event, all members of the dwelling unit, or all occupants of the dwelling unit, can go into that space and stay safe. And what this is cooling to one room or space only. It can be the living room, it can be the bedroom. It's meant to be a refuge. And as noted for the requirement, don't exceed 26 degrees. It's your obligation at building permit to tell us how you will not exceed 26 degrees. generally this is mechanical cooling. It's going to be some format of that. I don't have any examples in here. That could be mini split. You can answer outside and your unit inside in the living room or bedroom. It could be a PTAC, I suppose. You show us. And lastly, we highlight this is fully possible through the BCBC requirement, passive cooling. What this also means is no mechanical cooling. Now, if you do decide to take that path, you're fully enabled to. And this is the key here, note 26 degrees must be demonstrated to be not exceeded in any in at least one space, okay, in the refuge room. I also want to highlight, and this is again back to modelers or everybody in the room really, but I also want to highlight that this 26 degrees requirement comes from 933.3.1 bracket 2. This is completely in parallel and separate from the energy modeling guidelines of the 200-hour limit through step code. So the second bullet there says City of Vancouver energy modeling guidelines 200 hours limit. Those mandatory calculations are not relevant. They're not. They could overlap, but just acknowledge they're not the same. Okay. So when you are demonstrating your living room, master bedroom, and say, hey, listen, this is not going to be 26 degrees or higher because this overheating limit through ASHRAE has been demonstrated. They're not the same. We do need documentation, which will usually, we're guessing, we haven't seen this come in. We're guessing through its very sophisticated energy modeling or thermal modeling that shows that in that space, no molecular air surpasses 26 degrees at summer design. Okay, in summary, for Part 3 Type C buildings, one option is central cooling, or cooling all areas of the dwelling unit. You have a central air conditioner or central heat pump that is automatic compliance. Use a heat pump to also provide heating and cooling that supports your step code requirements and your zero carbon step code requirements if the municipality you're building in requires that. And in the Township of Langley, we are at for Part 9 we're at EL2. That's this that item 3. Item 2, EL2 and up is particularly for Part 9 buildings for us, as well as it does apply in Part 3. The second item is local cooling, or also called a refuge room, or also called cooling a space. You can use a mini split or whatever you like. The sizing, and that's important, the sizing or on controls must be conducted to meet the 26 degree limit or better, colder, I suppose. And when you are designing it, this is for your modelers or other design folk, whatever space you choose, you want to model it as an enclosed space, okay? As noted, and that's the key, this is a key thing here, it's important to acknowledge the 200-hour limit may still apply. And lastly, passive cooling. If you want to take that approach, go for it. You will need to submit an energy modeler report, and that's going to demonstrate that you're not going to exceed that limit. I want to make some key points here, and this is the same for Part 9 for those who build both. Operable shading, your window blinds in the middle, that patio are not to be used as a compliancy measure. Okay, those are user operated. If you're not able to use them or they're not operating, they will not provide any kind of deflection of the sun. Thereby, operable shading is not going to be, you cannot model that as a part of your compliancy. However, fixed shading or their fixed measures can be included. Of course, the report will be signed and sealed. Okay, that's it for me for the overheating for Part 3 compliance. If you do have questions, you can put them in the chat or email us at greenbuildings@tol.ca. You're making excellent time. So with that, I'd like to introduce our main speakers of the day. That's Jack Kui, Ziken Wang, and Andrew Peacock of JRS Engineering. So Jack is a senior building science specialist and division manager of energy services at JRS Engineering. He has a ton of experience on these matters and he's sharing that with you today. Ziken Wang is an energy modeler at JRS Engineering. Zikun brings 3 years of experience in energy and sustainability consulting. Modeler who can really kind of tell you the ins and outs, what happens at the design stage. And Andrew is a project engineer at JRS Engineering and brings 7 years of experience in structural engineering and building science. And he's going to be able to talk to you about some of those practical applications of how to ensure your building envelope is as airtight as possible. So with that, I'll hand it over to JRS Engineering. Take it from here. Thanks, everyone.
Great. Thank you, Kevin. I'll be starting share my screen. Awesome. So good morning, everyone. Welcome to our presentation on energy and air leakage analysis. We are excited to share some insights that we have learned from the study, and thanks for joining us today.
Zeke, you are muted.
So can you hear me well?
Yes.
Okay, sounds good. I just want to give you a quick introduction. Kevin did already. So I'll be presenting with Andrew here, and our division manager, Jack, is also here with us. He will be on standby to answer some questions just in case. A little bit about JRS. We are a building envelope and building science firm serving Western Canada. Since 1997, we have worked with our clients to create high-performance buildings that are durable, energy efficient, and cost-effective. Our expertise in building science combined with a practical understanding of construction allows us to deliver tailored solutions for projects of all sizes and complexities. At JRS, we specialize in 5 key areas: new construction, energy sustainability, roofing and waterproofing, existing buildings, fenestration, expert engineering. Within each area, we offer a wide range of building science services from early schematic design, energy modeling, and sustainability consulting to post-construction warranty reviews, assessments, and repairs. As a full-service building science firm, our multidisciplinary team works together to deliver integrated, seamless solutions across all divisions. Early this September, JRS Engineering was engaged by Township of Lanley to study how increased airtightness test results will impact your step code compliance for Part 3 residential and commercial buildings. The goal of the study is to provide insights that help the industry design and construct buildings that can mitigate air leakage risks, ensuring developers can meet and even exceed the energy requirements. So, how does compliance with the step code work? I'm sure most of you have come across with a BC building code before, BC step code before. So let's take a quick look of how this works. Just to remind you, energy efficiency compliance for BC step code buildings is a performance-based rather than prescriptive. That means the focus is on meeting some measurable targets rather than following a fixed set of rules. So for energy modeling, we evaluate 2 key metrics: thermal energy demand, or you can call that TEDI, which reflects the energy efficiency of the building envelope; total energy use intensity, which is called TED2E, which measures the overall energy consumption. Each step of the code have its own targets for these metrics, which vary depending on the building type, such as multi-unit residential buildings or MURBs, office buildings, or retail malls. Another critical component is airtightness testing. The energy modeling stage, the target is set to no more than 0.2 liter per second per meter squared at operating pressure, as required by the BC code. The target is then verified after the building is constructed. So the key takeaway here is that the compliance requires both accurate energy modeling and successful airtightness testing. Together, these ensure that the building meets or exceeds the specific performance targets for the step or the building type that your design is categorized into. Now let's quickly walk through the process of energy modeling for ensuring energy compliance under the step code. So it starts with energy modeling with an assumption of air leakage value at 0.2. And this step evaluates the building's performance using two key metrics, TUE and TADI. We have just talked about that. In general, TADI is more challenging to meet as it heavily depending on the building envelope's performance, basically how well your walls, windows, and insulation are performing. So once energy modeling is complete, the next step is obtaining the building permit, followed by the construction phase. After construction, the airtightness testing becomes essential. This test ensures that the building meets the airtightness target of no more than 0.2 liter per second per meter square at operating pressure. So the results of these airtightness tests are critical because if the building passes and meets all the energy targets, the occupancy permit can be issued. If it fails, further steps will be required to address the issues before occupancy is granted. It's important to remember that meeting these energy and airtightness targets isn't just optional. It's required by the law. It's required by BC Building Code. That's why managing airtightness risks proactively is very important. Failures in airtightness testing can lead to energy non-compliance and may even prevent the product team from meeting step code requirements and faced with other technical challenges. And we talked about how important TADI is, so we cannot overstate the importance of the building envelope. The envelope usually includes walls, windows, roofs, foundations, acts as the barrier separating the inside of the building from the outside environment. It plays a key role in determining how much heat is lost or gained. That's why it's dominating the TADI or the thermal energy demand. Airtightness, on the other hand, presents a unique challenge. It's not just about sealing a few gaps here and there. It's more a systematic thing. It relies on the entire building envelope working together cohesively. Even a small issue in one part of the envelope can largely impact the overall performance. And what makes the air leakage even more complex is its connection to the construction practices, how the building is assembled, how what materials have been used. The durability of sealing all together play an important role in achieving this target. And because airtightness cannot be easily corrected after construction, it's really important to address it during the design and construction phase. And just for your reminder here, we're using airtightness, and it's also called air leakage or infiltration, so we're using these terms interchangeably. So now we're clear that we want to focus on air leakage, and this is what the study is about. So during the energy modeling, we assume an air leakage rate of 0.2. With this assumption, we calculate TADI and TUE targets and needed to meet the energy requirements of the step code. The challenge, however, is that we don't know the actual air leakage until the building is constructed. And then we perform an airtightness test. So this creates a risk. The actual test result may not align with the assumption we made during the energy modeling phase. Potentially, that will lead to non-compliance with the step code. So the goal of the study is to understand this risk and to identify strategies to reduce it, ensuring that the building meets the airtightness targets and still remains compliant with the energy requirements. So with that context in mind, let's dive into the methodology and some of the key findings of the study, especially focusing on air leakage and its impact on energy performance and energy compliance. So as part of the beginning of the study, we selected and studied 6 different building archetypes. They are chosen in the context of Township Landy in order to gain a deeper understanding of air leakage and how it's impacting the energy consumption and energy performance. These include a 6-story, a 13-story, and a 40-story multi-unit residential buildings, or we call them MERBs, as well as a 5-story office building and a 1-story street mall. What you can see here are some simple outlines of each building type. And below is a methodology we have used in our study. Basically, we started by designing the buildings to meet step code at step 2, 3, and 4. Step 4 is only for MERPs, by the way. And we're assuming an air decay rate of 0.2 liter per second per meter square at operating pressure, according to City of Vancouver's energy modeling guideline. Next, we analyzed the impact increasing air leakage at incremental steps of 25%, 50%, 75%, 100%, and even 200%. For each model iteration, we assessed how these changes affect the two key parameters we talked about, TEDI, the thermal energy demand, and TUE, the total energy use intensity. So by examining these variations, we have gained valuable insights into how air leakage could impact energy compliance under the step code. As we develop these energy models, we have made several assumptions about construction and building details. For conventional construction, we assumed a 2x6 wall with vinyl windows. For wood frame residential buildings. For high-rise residential buildings, we have assumed window wall systems. For office and retail buildings, we assumed concrete construction. We also considered a range of variables to meet different step code targets because we're trying to do step 2, 3, and 4 designs. So these variables including mixed of vinyl and metal windows for high-rise residential buildings, change of window sizes to adjust the window-to-wall ratio, and using of more advanced building envelope and detailing to improve the overall thermal performance of the building envelope, and better ERVs, energy recovery ventilators, to improve the heat recovery efficiencies, and different mechanical control strategies, etc. I just want to give some extra credit to our division manager Anton here about the use of mixed vinyl and metal windows for high-rise residential buildings. These are very interesting skills and techniques that we have used in our energy modeling practice here. And so overall, I want to mention that it's important to note that a building's energy performance depends on many factors. The goal of the study is only to provide valuable information for designers' consideration. We're not trying to present a one-size-fits-all or cookie-cutter solution for the industry. So in the following slides, I'll be presenting the results through several key charts, which will demonstrate the impact of air leakage on energy performance. The first set of charts, we will be talking about TEDI and its relation to air leakage and how that will be impacted by a factor called VFAR. Vertical surface area to floor area ratio. We'll talk about that in more details. The second set of charts we have here is for TUE and its impact with air leakage and how the heating efficiency play in this relationship. And then lastly, we'll talk about how much tolerance we can get for air leakage increase. Okay, let's look at the first chart. This is showing the relationship between TEDI and air leakage increase. So on the x-axis, the air leakage increase is showing at 25%, 50% to 200%. On the y-axis, we're showing how TEDI is being impacted by that. And just for your information, the TEDI target is showing by the horizontal dot lines on the charts and also showing on the table on the right-hand side, just in case that you want to know. The first thing we can see in this chart is that TEDI increases as air leakage rises. It's pretty obvious. So this trend appears to follow a nearly linear pattern. That means that as the amount of air leakage increases, the thermal energy demand, or the TEDI, also increases in a consistent way. Now, if we take a closer look, let's take a look at 13-story MERP as an example. During the energy modeling phase, this building has a relatively small safety factor built in. If you look at that little dark arrow I put there, that's the safety factor we have for the energy modeling for this building. Now, because of this small safety factor, even a modest increase in air leakage, about 25%, caused the building to fail its energy targets. In contrast, the 6-story MERP, the blue line, which you see in the chart, has a much larger safety factor in its energy modeling phase. This allows it to tolerate a much greater increase in air leakage, up to 75%, before it starts to fail the energy compliance. So this leads us to a very important observation, which is also very intuitive, that the higher the safety factor is in the energy modeling phase, the greater the tolerance for air leakage increase will be. So a larger safety factor provides more flexibility, making it easier to manage air leakage while maintaining compliance. So if you wanted to leave more safety ranges for air leakage tolerance or air leakage increase after the construction, maybe you want to consider more safety factor at the beginning for energy modeling.
Hey Zeke, can I just jump in here real quick?
Yeah.
Just a note to the gang on the phone, and particularly this chart, and Zeke's going to go through a lot more of these really great charts. Just a bit of context from at least in the township of Langley. Zeke showed us this 13-story MERB with a relatively low kind of safety factor, and let's just say the 6-story MERB, which had a bit more. We're starting to see our Part 3 Type C buildings come in at final, and per BC, as a part of STEP code, it is required to do airtightness testing with a company like JRS or others, and create a report. The values in that report, as Zeke has noted, you are obligated to take the actual tested value and re-inject it into your energy modeling report and see what pumps out. While you are given a kind of placeholder value to use for your model, you are still obligated to update it. And Zeke and the gang are going to go through a variety of kind of results that they've seen out there in the wild. But the ones that we are seeing, and at least one particular one, which kind of spurred us to put together this talk with JRS, was the air tightness result of that one building ended up being nearly 100% higher than its assumed rate. And if we look at this chart here, in the case of, say, a 6-story MERB, 100% could have, depending on the safety factor, put it out of compliance. And this is a thing that exists in the BC, and we're all kind of chewing on this right now as we start to see buildings come in. But it is important to acknowledge at least some of these values that are possible to come in can literally put you out of BC compliance, basically right before you're calling for final, which is why Zeke and the gang are really going to go through this. But I just wanted to provide some context here that the slippage rates, or whatever you want to call it, can be significant depending on how, what kind of practices you have or what kind of safety factor you include. But we have seen some values that can be rather concerning. So the numbers here, Zeke, are showing you. Yeah, please please be aware of kind of where you what your current results are, and kind of what that can result in if your slippage is too high. Okay, thanks, Zeke.
Yeah, thanks, Kevin, for the comment. So it's definitely important to keep in mind the safety factor at the beginning, if just to mitigate the risks for air leakage increase later on. Now, on top of that, another interesting aspect that we have identified is the slope of the lines. For example, if you look at the charts, as the air leakage increases, the TEDI of the strip mall rises faster than that of the office building. In other words, the strip mall TEDI is more sensitive to air leakage and is much more sensitive. So it has it's really impacting against the air leakage increase. But why is that? So this is a very interesting and important question to consider here. We're going to dive into that further in our following slides. But before we do that, I just want to quickly show you the step 3 and step 4 charts we have here. So for higher step designs, we have found similar trends, similar as step 2, and similar conclusions. So this kind of reinforcing the consistencies between these findings across different step code levels. Okay, now we come back to that question. So to understand why the strip mall is more impacted by air leakage, we have examined a very interesting factor called the VFER, the vertical surface area to floor area ratio. This is we call that building shape factors. It's a measurement of the building's shape, and it's influenced by many design choices, such as if you have more exterior surfaces or higher ceilings, then you may end up having a high VFER. Again, we're not trying to say low or high VFERs are better or worse compared to each other. Just these are design choices, so we want to rely on the architects or developers' opinion or options on determining what the building looks like. But again, if you have a different VFER from the general category, then maybe keep that in mind just in case that it cause some additional impact on the air leakage. So in our analysis, we found that the strip mall has a significantly larger VFER, about 1.2, compared to the others around 0.5. So this larger ratio means that more exterior surface areas relative to the floor area, meaning it's going to lead to greater heat loss and making the building a little bit more sensitive to air leakage. So to give you a more visualized impact relationship between these two, here we have plotted the impact of air leakage on TEDI against different VFERs. Basically, for flat buildings, we can have five VFERs, and you can see for the strip mall, it's really far away from the others. So it's having a much larger VFER. At the same time, it's having a larger impact of air leakage on TEDI. So we have come to a really interesting and also important conclusion here, that the higher the VFER is, the more impact the air leakage will have on your TEDI. The trend applies to all building types, not just strip mall, because it's based on 5 building archetypes that we have studied. And it highlights that buildings with a larger VFER are more sensitive to air leakage increases. In other words, buildings of a higher VFER have relatively less tolerance for air leakage failures. The slippage rate is lower. So if your design has a high VFER, it's important to keep this in mind. And additionally, if we overlay the trend line for higher step code levels on top of this, we see a similar trend, but slightly less impact, indicating that if you are designing a building for higher step, this can somewhat mitigate this sensitivity, but it's not very much. Okay, so those are for TEDI and air leakage. Now let's take a look at how TUI and air leakage are interacting with each other. To study that, we have generated similar charts as those of the TEDI, showing the relationship between TUI and air leakage increases. Here we can see at step 2, TUI almost stays within compliance, even with the 200% increase in air leakage. Right? So MERB, the target is 130, off-phase target is 110, mall is 145. All of them are within compliance, even you have 200% increase. However, if we go to step 3, MERBs begin to fail compliance. MERBs begin to fail compliance when air leakage increase to about 75%. Now, step 4, the slippage tolerance decreases with compliance failing at approximately 50% increase in air leakage. Now, that being said, general observation we have here is that TEDI follows similar trends as that of TEDI. So we see a linear trend, how TEDI is responding to air leakage increase. And also it's showing us greater tolerance for air leakage increase. So basically, that being said, for the buildings we studied, and for most buildings in general, when air leakage increases, TEDI will fail first, followed by TUI. This makes TEDI the critical metric to watch when managing air leakage and ensure energy compliance. Now here, I want to show you a comparison between TEDI and TUI. So if we look at these two charts here, on the left is impact air leakage increase on TEDI versus air leakage increase, and on the right-hand side is for TUI. If you focus on the strip mall here, you can see the strip mall shows a much flatter trend in TUE as air leakage increases. This difference comes down to the heating system used. But the strip mall is using a heat pump technology, while the MERBs are relying on electric baseboard heaters. But since the heat pumps are significantly more efficient, it's using a COP, than baseboard heaters, the impact of air leakage on TUE is less pronounced. In other words, the more efficient the heating system is, the less impact air leakage increase will have on your TUE. I just want to quickly comment on that since we're using heat pump a lot right now, and also at the same time, your TEDI is the leading factor in achieving energy compliance. So TUE seems relatively less important, but still something to keep in mind if you have a not really efficient system. Now, lastly, let's take a look at how much tolerance we can achieve for air leakage increase. As we mentioned earlier, since energy modeling compliance is largely dominated by TEDI, so we'll focus on that here. The tolerance for air leakage increase before failing energy targets, depending on two key factors. The first one is the safety factor we have used for initial energy modeling. Talked about the larger you have, the more slippage tolerance you can have at the end. And also, if you have a design VFER that's really high, keep in mind that may create more risks of air leakage increase during the final testing. So this may reflect on if you have a complex building shape, many exterior surfaces, maybe you have a really narrow design, such as a building infill, and then maybe for some commercial spaces where retail malls that you have extra floor height, high ceilings. These could contribute to a high VFAR that may lead to some extra consideration when it comes to air leakage testing. Now, by accounting for these factors, we can better manage risks and improve compliance outcomes. Here, I was able to get some tables outlining the expected tolerance percentage for air leakage increases. I'm going to give you an example here how to look at this table. For example, with a VFER of 0.2, which is really common for most buildings, the energy model for MERBs can handle about 24% of air leakage increase at step 2 and about 17% increase at step 3. For office buildings and retails, the tolerance is about 16% and 11% respectively. It's important to note that if your building has a higher VFER, the tolerance can be significantly lower. If you look at, if you have a building design as a VFER about 1.0, then your tolerance for air leakage increase will just be reduced by over 50% compared to a design of VFER equal to 0.5. Great, so these are all the key findings of our study. I hope you find those information useful. Now I'll hand the presentation over to my colleague, Andrew. He will be going through some recommendations and case studies in more details. Thank you. Andrew.
Thanks, Z. I'm just going to lower the camera here so you can see me. Okay, so yeah, we went through some really good information about energy modeling, including a safety factor, and also some considerations for the building shape. And what I'm hoping to go through today is just some of the key aspects of the air barrier system, architectural details to be able to capture these critical detailing locations in the design stage, and then also what to expect during construction and at final construction when we're going to be conducting air tightness testing. So I'm sure many people have gone through the process of air tightness testing by now. But yeah, really what we're looking for or looking at is a dedicated air barrier system. So the air barrier should be designed to last the lifetime of the building, or at least the materials that are covering it, like the cladding or roofing. And the continuity is really the most important aspect of the air barrier. If we don't have continuity, then there's a clear path for air leakage. It can also be the most challenging to achieve because there's going to be lots of penetrations through those air barrier materials. That includes, vents, lighting, electrical, even cladding attachment. So the other things to consider are strength and stiffness of the air barrier material and also the durability. So we're looking at, is that material adhered to the substrate? What are the forces on the air barrier, whether it's vapor control, wind, moisture, making sure that those materials that we're using are going to withstand those forces and continue to perform as an air barrier. And so, considering all of those things, material selection does also have a huge impact on performance when it comes to airtightness testing at the end of the project. I'll get into that a little bit more, but generally, you can kind of see from these graphs or these photos on the right, an exterior air barrier approach where we have a continuous air barrier on the outside, whether that's a moisture barrier or roofing. Having that on the outside will generally have fewer penetrations than using something like a polyethylene on the inside, where you're going to have lots of interior penetrations like vents and lights. And yeah, so kind of like I was mentioning, the detailing is really critical when it comes to the air barrier system. When we're dealing with an exterior air barrier approach, we do still have penetrations. There are still going to be, ducts, vents, roof stacks, all penetrating through that air barrier. But this is really where the material selection and detailing on site comes into play. Not only is it important to capture these details in the design phase, especially in architectural drawings, where the people on site are going to be looking to those drawings to identify or figure out what to do, but also the actual detailing that's conducted on site is going to play an important role when it comes to airtightness. So materials like a Tyvek, it's going to rely on tapes and sealants to be able to perform as a continuous air barrier, whereas a self-adhered product will have a little bit more redundancy. It won't be relying on those accessory products. And I also just want to touch on something that we previously mentioned when it comes to that vertical surface area to floor area ratio. A simpler shaped building like the one in this bottom left photo, not only will it have a lower VFAR, but it will also generally perform better because it has fewer details, fewer complex details. So this building on the bottom left, it doesn't have balconies. It has fewer exterior doors. So much simpler detailing, much simpler air barrier transitions between wall to roof, wall to window, compared to the building on the bottom right. This building will likely have a higher VFAR, which means that not necessarily that the higher VFAR is a worse design, but it will be impacted more with a higher air leakage rate. And as we can see, we have balconies, we have canopies, roof decks, dormers, just many more complex details that will make the continuity of this air barrier more challenging. And so getting into the airtightness testing, as Kevin has mentioned previously, airtightness testing is a requirement of the BC Building Code. So it's required for all buildings across BC. I'm sure many of you have gone through the airtightness testing process by now, but what we're looking at is essentially pressurizing and depressurizing the building up to at least 75 pascals. The BC Building Code also, the intent of the BC Building Code is to test the building envelope and not necessarily airflow through mechanical systems. And so when we're preparing for an airtightness test, we're actually going to be sealing off all of those intentional openings like HVAC, whether that's ERVs, whole building HVAC, even laundry exhaust, kitchen exhaust, all of those should be getting temporarily sealed for the test so that we're not measuring that airflow Also, when it comes to building prep, we want to make sure that all of the windows and doors are closed, and mechanical ideally would be turned off so that it's not blowing any of that temporary seal off of the vents. And then a few things to expect on site when it comes to the day of testing. Trades really need to be informed of what's going on so that they're not, accidentally interrupting the test. So people can't be moving in and out of the building during a test. Obviously, we want to make sure that that building envelope is closed up, and so we can't have people opening doors during a test because that will impact the airtightness result. And it should go without saying, but shouldn't be drilling holes through the envelope either during a test. Seems pretty straightforward, but unfortunately it has happened in the past. So just a few things to keep in mind. And I do just want to touch on mid-construction briefly. I know that it's not a requirement right now for Part 3 buildings in most jurisdictions, but it does have some, it does provide some really good insight to the performance of the air barrier detailing, the performance of the building prior to testing at final. So there's a few different approaches when it comes to mid-construction testing. Air tightness testing of the whole building at mid-construction is an option, or even if it's just a few floors, we can measure the air leakage rate of those few floors of the building and compare that to the energy model target that you're going to be trying to achieve at final construction. And based on that that result that you achieve at mid-construction and how close that is to your energy model target, you can determine whether or not you need to make any additional or take any additional measures to ensure that you're going to comply at the end of the project. Ideally, you'd have the air barrier exposed at your mid-construction test so that any repairs can be conducted if needed. And another really helpful tool is air leakage investigation. So that might include, pressurizing or depressurizing the building and walking through to try and feel for any sources of air leakage. But smoke testing really is, I think, one of the best visual indicators of where there might be air leakage occurring through your building envelope. So you can see in the top left-hand corner, we were pressurizing this building and filled a few units with smoke, and because that building is being pressurized, it's trying to push that air or that smoke through the kind of easiest path of air leakage. And so in this case, we recognized that there were some vents that did not get sealed up properly. But in the top right, we can also see that there's some obvious building envelope details that either weren't detailed correctly or didn't account for air barrier continuity in these locations. And then thermal imaging is another great tool. It does rely a little bit more on having a greater temperature difference between inside and out. But the approach is kind of the same, where we're pressurizing or depressurizing a space and using that thermal imaging camera to identify any sources of air leakage. So yeah, these methods, again, not required right now by code, but they're a great way to ensure and provide some quality control during construction. Now, based on our experience in testing and providing this kind of air leakage investigation, some of the common air leakage locations that we've noted are kind of listed here. One of the biggest ones is building preparation. So if you can imagine, you're testing a 10-story building, and let's say some of the vents don't go or don't get sealed on a couple of floors. That's, if we're talking about vents, that's, a 6-inch hole through your building envelope in a number of suites. So huge amount of air leakage can occur if some building prep goes unsealed. Also looking at assembly transitions. So your air barrier continuity from wall to roof or wall to balcony, wall to window, all of those details do come in to play. And then some of the other kind of major air leakage observations that we've made is through some operable windows and doors. Generally, that is going to be commercial entries, which have a poor air leakage performance. In the top right-hand corner, this one is actually on a car dealership, so it's not really intended to perform as a great air barrier. So if your buildings do have these assemblies, just important to consider that in the whole building design. A few other things: cantilever joists and fluted decks. Not that these are particularly poor designs, but it does create challenges with air barrier detailing. So with cantilever joists, for instance, it doesn't allow for pre-stripping an air barrier behind those cantilever joists. So instead, what has to be done is actually detailing your air barrier around each and every single one of these joists, which is labor intensive and also quite complicated. And same goes for fluted decks, having to detail your air barrier material onto that kind of Q deck. So not only is this kind of important to recognize during construction and provide some enhanced detailing, but also to capture that in the design, whether that's architectural design or detailing, capturing that in the design and recognizing those complexities. Okay, and I just wanted to go through some data. I think this is some really valuable data that we've been able to collect. We can see this is for Part 3 buildings, and it's the airtightness performance of Part 3 buildings based on the air barrier material or air barrier system that they've used. So on the x-axis, we have the result under pressurization, and on the y-axis, we have the result under depressurization. So the location of these dots is kind of the average between pressure and depressure results. So I'm also going to pull up here. These lines are representative of what a typical energy model input might be for a Part 3 building. Obviously, this doesn't capture all projects, but in a lot of cases, we're seeing an energy model input of maybe 1 to 1.5 liters per second at 75 pascals. And this is really important to kind of clarify. When we're air tightness testing, our results are measured in liters per second per square meter at 75 pascals, and this has to be converted back to operating pressure for the energy model. So we're talking about the same kind of measure, just at different pressures. So when I'm saying a typical energy model input might be between 1 and 1.5 liters per second at 75 pascals, that's equivalent to 0.2 at operating pressure. Just depends on the building shape, building size, things like that. So trying to kind of read this chart here, building or these points that are to the left of these typical energy model inputs, they are compliant with the energy model. They're meeting the airtightness target, and so the energy model is compliant. Any of these dots up and to the right of these typical energy model inputs would fail to meet the airtightness target, and your energy model would no longer be compliant. So another great reason, like Z mentioned, to include a safety factor, because we can see quite a few dots not meeting these typical energy model inputs. Again, these energy model inputs will change depending on your project, but this is just kind of representative of a typical input. I also want to speak to the different air barrier materials here. So in green, we have an airtight drywall approach, which is an interior air barrier. In blue, we have a self-adhered membrane, which is an exterior air barrier combined with polyethylene on the inside. In yellow, we have a Tyvek with taped seams on the outside combined with polyethylene on the inside. And then in the kind of brown red, we have a window wall and curtain wall assembly. And I do just want to kind of qualify the window wall and curtain wall assemblies. I was actually a little bit hesitant to include these in our graph here, but testing of these types of buildings are going to be on, high-rise buildings. That's typically where we see window wall, curtain wall. And to date, we have very few kind of data points for these types of buildings. Even though the step code came into or was a mandatory requirement by code a few years ago, these buildings are only just, coming to, final completion and are just starting to be tested in the past year or so. So we don't have a lot of data points, but there are also some different complexities to these types of buildings compared to, say, a mid-rise or a low-rise building. Some of the trends that we're seeing, you might be able to see, a lot of the blue dots further down to the right, yellow kind of in the middle. And like I mentioned before, this comes down to the material selection. So a self-tiered product will generally perform better than a sheet product like a Tyvek because it allows for some redundancy in detailing. It's actually adhered to the substrate and it doesn't rely on tapes and sealants, and will generally be a little bit easier to detail when it comes to your air barrier transition details from wall to roof. It just adds some redundancy to those details. Another kind of key point here, there's a small group of buildings to the very bottom left which have performed very, very well, generally below 1 liters per second per square meter at 75 pascals. Normally I would kind of ask the group what they think creates this kind of bubble of results, but I'm just going to kind of get straight to the point. These buildings are generally a simple shaped buildings. The majority of these results are modular buildings where the simple shape, really standard kind of simpler detailing will improve your results. So this group of buildings here is a simpler shaped building, and so you can kind of see how important some of this detailing and shape of the building can be when it comes to airtightness testing. And one more quick thing that I'll also point out, I've added a dashed line to the graph here, and what this is it's representing if your pressurization results are the same as your depressurization results. So this line, if your dot is on that line, your pressurization is the same as your depressurization. But what we're seeing, the trend here, is that most buildings actually perform better under depressurization than they do under pressurization. And what that typically means is either there's more airflow occurring under building pressurization. So air is is being pushed out of the building. And when that is occurring, in a lot of cases, what we're seeing is either windows and door gaskets are no longer engaged because the building pressurization is kind of pushing those windows and doors out. Or in some cases, we actually see a lot of air leakage through ducting. So even if vents are sealed from the inside, there may be air leakage through the ducting, which is going out through exterior vents that might not be accessible. So again, these window and curtain wall buildings, these high rises, we may be able to seal these vents from the inside, but accessing vents from the outside is going to be really, really tricky to do. And so if we're pressurizing the building, unfortunately, there will likely be some air leakage through the ducting. So it's important to account for that, like we've mentioned, with a safety factor in your energy model. And I'll just go through a few case studies as well. This first project here is called the Melrose. It is a high-rise building. I believe this was 33 stories. It uses a window and curtain wall system, as well as a self-adhered membrane across a number of wall and roof assemblies. We were the building envelope consultant as well as the energy modeler on this project, and we conducted some mock-ups during construction for air barrier detailing as well as building prep prior to testing. And this building actually had a safety factor of 32%. So the energy model used a air leakage target of 1.38. When it came down to testing, again, a lot of vents, you can see on the right-hand images there, there were some vents that were accessible to be able to temporarily seal, some weren't accessible. So at the end of the project, we did the airtightness testing and we achieved a result of 1.93. So this is obviously much higher than the target, but because the energy model had a safety factor of 32%, this building still complied with the TEDI and TUI targets for BC step code. So this building did end up passing. The next case study here is called Living. It's a 6-story wood frame building. It uses primarily a self-tiered exterior air barrier as well as polyethylene on the inside. I believe this one actually uses a polyethylene air barrier at the kind of ceiling level or the roof level. And for this project, we were the building envelope consultants and the air tightness testing agency. We actually conducted some mid-construction air tightness testing on this building and some smoke testing. So we were able to identify some of the either deficiencies or areas of air leakage at mid-construction while the membrane was still exposed to be able to, conduct repairs. We could provide recommendations to the contractor to conduct repairs where needed. And when it came to final testing, the target was 1.1 liters per second at 75 pascals. We tested the building and achieved a result of 1.48. So unfortunately, this did not meet the energy model requirements. And so we had to do additional air leakage investigation. We did some additional smoke testing to try and identify where air leakage was occurring. And what we found was that there was air leakage occurring through the ducting. So it was actually, smoke was exiting through exterior vents. And so the contractor went back and in addition to sealing up those interior vents, they went back and sealed the majority of the exterior vents as well. And so when we retested, we achieved a result of 1.1, which complied with the energy model requirements. And last case study here, it's called the Man 6 building. This is an office building in Vancouver. So as you can see, very simple shape. It's also, it's an office building, it's not residential, so there's fewer penetrations, fewer operable windows and doors, balconies. So very simple detailing, but also uses high-performing air barrier materials. So it's a self-tiered membrane product and uses, high-quality windows and doors on this project. There was a target of 2.0 liters per second in the energy model. And when we tested the building, we achieved a result of 0.72. So a much, much better result than the energy model target. And that I think is thanks to not only building prep, but attention to detail during construction as well. Okay, and I'll hand it back to Z for a quick summary.
Thanks, Andrew. So let's quickly summarize the presentation we did today. So building envelope performance is really critical to energy compliance. The TEDI target, which depends on the building envelope performance, is usually the key in energy compliance. Therefore, we must ensure that the building envelope inputs are correct. And a key finding that we have here is that the more complex the building shape is, where the higher the VFAR is, the more impact your air leakage increase will have on TEDI and TUI. And also for TUI specifically, the more efficient the building is, the less impact it will have on TUI. But just keep in mind, in most buildings, TEDI will be the dominating metric that we should give special attention for. And lastly, energy non-compliance risk due to air leakage reinfiltration exceeding the model value should be addressed early, as I mentioned in the design phase, and Andrew mentioned the construction phase, through either designing towards better prediction for infiltration failures, or doing more construction quality control in the construction phase. And thank you all for attending our presentation. And I want to give some extra credits to Kevin, Jean, and Carol from Township Landy, and also our internal team, Hai, Fong, and Anton, on providing valuable insights and assistance in the work. I think that's the end of the presentation, and I want to introduce all of you to the question and answer session.
Thanks so much, Zeke and Andrew. That was a really informative presentation, and certainly technical and a lot of great data. So I think now is a great time for the room to post your questions in the chat. Kira will kind of facilitate for the first few that's that's already here in the chat. And as we're going, you can put your questions there in the chat, or if you wish to ask a question live, please do, and you can do that by putting your hand up. At the top of your screen, there's a hand image or icon that says raise. If you put that, we'll be able to see that, and then Kira can kind of unlock you, and you can ask a question directly to our consultants. Right.
All right. Does anybody want to ask their question live, or?
Well, I think we'll let them put their hand up first, and we'll go through whatever's left in the chat first, and get through those chat questions, and then we can go to the live questions if they do pop up.
Okay. I'm not sure which questions have already been answered in the chat or through the presentation yet. But, do you want me to just read all of them, or?
I think we can start with Arjun's question from 931.
Oh, okay. So Arjun asks, regarding air leakage testing, who is responsible for confirming the leakage rate at 75 pascals? Is it the energy modeler or the person performing the testing services? Also, can you elaborate on the threshold of 2 liters per second per meter squared? We've had a few projects that we've performed tests on, and the requirement is sometimes as low as 0.8 liters per second per meter squared due to the initial assumptions made by the modeler. A lot of buildings won't end up meeting the stringent of a requirement. Do you have any tips for modelers and builders?
Yeah, so I can speak to that. And yeah, I spoke to this a little bit, but the person confirming the airtightness results at the end of the project are going to be airtightness testing agency. So not the energy modeler, unless the energy modeler is also doing the airtightness testing, but typically it's going to be whoever's testing the building is confirming that airtightness result at 75 pascals. And then I spoke a little bit about the threshold. I think that's meant to be 0.2 liters per second per square meter. That 0.2 liters per square meter is at operating pressure, and that gets converted to a measure at 75 pascals. And we compare that to the tested rate. So this will change depending on the shape of the building, the size of the building, and some other aspects. So like you said, sometimes a project might have a target as low as 0.8 liters per second per square meter. And, that's equivalent to 0.2 at operating pressure. And it really comes down to, the shape of the building, the design. And so really what we're hoping to achieve here is, if you have a really difficult target to meet, you really have to pay close attention and consider higher performing air barrier materials, ensuring that these kind of aspects are considered throughout the design. So air barrier continuity, making sure that all of these different details are accounted for, and also considering, any other safety factor that you can include in your energy model to account for an air leakage increase. If you test at the end of the project and your result doesn't meet that, you might hope that there is a safety factor included in your energy model. I hope that answers that question.
I'd like to add to some Andrew's comments here. If I kind of gather this right, the question from Arjun that the design team decided to kind of use an assumed rate, which was far lower than what we usually see as 0.2 liters. That's fully compliant. You're allowed to do that. You're allowed, if it says, use a placeholder value of 0.2 liters and model around it. And Andrew and Zeke said, go ahead and do that, but you probably want to have a safety factor if you're kind of new to the game, and that's good. But you can also just reduce your assumed rate, and that will kind of make your building perform a lot better at building permit or design. Now, if you do that, I just want to make it clear, you can do that, but you're assuming your building will perform that well. And so you are making yourself a bit more vulnerable, or significantly more vulnerable to failure at final. So do talk to so when you're formulating your plan with your modeler, do engage with your envelope specialist and talk about, how realistic are these values, and is it going to work for you? And if you wish to, and just as Andrew said, if you wish to have a really aggressive value to make the numbers work, then yeah, your material selection may change, and you need to have these discussions and make agreements, at this kind of planning stages. Or it's very possible, if you do not practice any of those kind of steps, that at final you are in for a surprise. And per BCBC, you are required to update your model with these new values, and there could be some significant challenges, when you really don't want to have them.
Yeah. I'll also add just one more quick thing. There are other aspects of the building envelope that you can consider modifying in your energy model to try and provide a little bit more tolerance, changing the mechanical system, or taking a look at the fenestration systems. Those have a huge role as well in the building envelope. It's not just air leakage. And so having kind of an integrated design approach will really make a difference as well.
All right, thank you. Next question. I think Alan's question about the strip mall being more sensitive, that was already answered during the presentation. James asks, if I understand correctly, when air testing is done, only selected spaces are tested and issues fixed for those areas only to improve results. Is it safe to say that there is still room for inaccuracy for the whole building in final testing due to the construction inconsistencies? If so, do you foresee the possibility of the whole building testing requirements in the future?
So I'm just trying to understand this question. If so, so currently, whole building testing is required at final construction. It's not testing, portions of the building. It's the entire building. During mid-construction, you might consider testing, portions of the building, but at final construction, you are testing the entire building as a whole. In some cases, if you have a large building like a tower, you might be testing it in multiple zones or portions of the building at a time, but you do have to test the entire building. So yeah, ideally, if you're conducting mid-construction testing of only a portion of the building, and you recognize that there are some deficiencies or areas where enhanced detailing is required, you would conduct that enhanced detailing across the entire building, not just in that zone you tested. I'm not sure if that answers that question, but.
All right, great. Next, Johnny asks, are there any data points collected from the renovation envelope? Would SA only without poly on the inside even work? How about smart AB or a vapor retarder?
Yeah, so when it comes to material selection, actually renovation projects, to my knowledge, are not required to test for airtightness. This is a new construction requirement only right now. I think, in the future, renovation projects will likely have this requirement as well, but currently not required. But then getting to the side of the question, talking about material selection, self-tiered membrane on the outside without poly would definitely work. But of course, it really depends on your wall assembly. A vapor retarder is required in wall and roof assemblies, and so you really have to consider what materials are acting as what part of your building envelope. Same thing goes for a smart air barrier or vapor retarder. These do work, but you have to consider, where are you going to be conducting your detailing? Is it going to be on the inside where you have to tape around every vent, every electrical wire through the polyethylene, or is it going to be on the outside where you have to consider detailing around ducts and vents?
Okay. Next, Amy asks, will the step code be updated to comment on very large single-family dwellings with or without suites that due to the building area and number of stories fall under Part 3? In Whistler, we require Step 3 and or Step 4 for Part 3 single-family dwellings.
Yeah. So I'm not sure what the update would be. I'm not aware, but yeah, there are a number of buildings that would typically consider Part 3, even townhouse buildings that might be over a single parkade that would actually typically be considered a Part 3 building. But really what I think comes down to is the testing approach or the testing standard that you're testing to. Actually, Amy just put her hand up, so maybe I can. Or should be updated.
Just seeing if I can give Amy permission. Oh, there you go.
Yeah, so I did. So Amy, you can unmute yourself and
Me?
please ask your question. Yeah.
Sorry, I'm just, I guess I could have rephrased that. The requirements for a Part 3 building are quite different from a Part 9.
Yeah.
And I guess my question is, do you think the code should be updated to reflect these large single-family homes? They're rare, but they do happen, where it lands in between a Part 9 and Part 3
Yeah.
building performance?
Yeah. Hard for me to say. Yeah, I do understand the difference. A Part 9 building is being tested to 50 pascals, whereas a Part 3 building is being tested to 75 pascals. So there definitely is a difference. Difference as well in the testing standard that's being used in some cases. But I think really what it comes down to is they're all trying to achieve the same thing, trying to ensure that air barrier continuity is maintained, make sure that these buildings are designed to account for air leakage.
Yeah, but there is some cost differences for energy modeling and having it reviewed by a registered professional versus using an energy advisor. But also you have to factor in TUI rather than MUI. So, it's kind of a gray zone, I think.
Right.
I was just wondering if you've dealt with that kind of building in your modeling for JRS.
I haven't. I don't know if maybe my colleague has.
Sorry, can you say the question again?
Just single family homes that fall under Part 3 in Whistler for bonus density, they have to meet Step 4 of the Part 3 for Part 3 buildings, or Step 3 for Part 3 buildings if there's no bonus density. And it is a bit of a gray zone because of the differences in a single family home with one dwelling unit versus, multi-occupancy, multi-residential type Part 3 building. And if you've experienced doing such modeling for single family homes under Part 3 step code requirements.
We have done multiple projects that looks like Part 9, but actually Part 3 due to the building area is exceeding 600, where number of stories not falling into category for Part 9. But what we did is basically just treat them as Part 3 buildings, like performing everything based on Part 3 step code, doing thermal weighting calculations, energy modeling, airtightness testing as such, because essentially they are Part 3 buildings. I don't think there are any additional comments on the speciality of these kind of buildings, like large single-family homes, as you mentioned. So the current standard just treat them as Part 3 building right now. Yeah. Thank you.
Thank you.
Okay, great. Next question is from Abbas. Has the township had to deal with occupancy energy model non-compliance on any Part 3 project yet, resulting from a failed air test or retest and no teddy buffer, lessons learned report, etc.?
Hey, Abbas. So yeah, thanks for that question. So the quick answer is no. As noted earlier in the workshop, I highlighted briefly an example that kind of motivated this entire works, where we saw the air tightness result kind of being doubled. It was still compliant, however, and that's because there was a buffer, and as well, actually, by chance, and kind of those on the phone who build these Part 3 buildings, they actually made some modifications, which is totally fine during construction, and this is around so it was, I believe, their window assemblies and maybe some other ones, which significantly had some significant impacts on their energy compliance, and so their buffer kind of plus their buffer, it worked out being compliant. So anyhow, the quick answer is no. But what your question is exactly what we're wondering is what are we going to expect to see, and that's why we got JRS to start doing these experiments through these models to see what happens at 10% slippage, 50% slippage, 100, even up to 200% slippage for a variety of building types to see how that impacts these results. So in that case where yeah, it was nearly 100% over, its air leakage kind of assumed rate, because they made modifications to their building envelope and they had a buffer, they were fine. But you know, as this team has notified, really you need to consider that during planning and not just going to hope for the best, because if you don't have a buffer and your leakage is poor, and if you did choose to lower your assumed value, you could be at risk.
Okay, great. Next, Johnny has another question. Going back to Zichun's earlier presentation on different building types and shapes, other than the VFAR, which makes sense, are there any differences in terms of wood frame versus concrete, especially for the 6 and 13-story MERB? Or is it still all depending on how well details are designed and get executed on site?
Yeah, thanks, Johnny. So apparently there are differences between wood frame and concrete construction, but if you're just talking about the impact of air leakage increase on TADI and TUE, theoretically they don't have any difference. But again, they impact your energy modeling a lot, especially for thermal bridging calculations, because concrete is more conductive and they usually get you low R values. So you may end up most likely with some less safety factor. Other things are the same if you assume, but again, it's very product specific. And then when it comes to the airtightness testing or air leakage control quality stuff, it all boils down to how well as you said, the details are designed and how the construction was managed.
Hey gang. I just want to kind of just jump in here. Hey folks, I do got to boogie a little bit early here. I know there's some great dialogue and great questions, and I think you'll continue doing these for a few more minutes. I have a Christmas event to attend with my daughter. So just before I leave, I just wanted to wish everybody on the call here a Merry Christmas, Happy Holidays, Happy Hanukkah, Happy whatever you practice during this winter season. And you can enjoy some quality time with those around you over the break. And we're looking forward to seeing you in the new year with lots of new products, workshops to share with you. So with that, I'll pass it back to Kira, and thanks for all joining. See you next year.
Thank you, Kevin.
Okay, great. Looks like we still have a couple more questions. So from Nicholas, 2 questions. I'll read them one at a time. The first question is, to date, have any Part 3 builders voluntarily chosen to do mid-construction testing? And the second one is, while there are a few data points, as you noted, window walls do not appear to perform well. Is this because of leaks between or within the individual curtain wall units?
Yeah, great questions. We'll speak to the first one. We have had quite a few Part 3 buildings choose to do mid-construction testing, especially high rises where this is a newer for most developers of high-rise buildings. So yeah, mid-construction testing is really valuable, especially smoke testing, to kind of assess the performance of the air barrier systems like window wall, curtain wall, but also on mid-rise buildings. It just provides really valuable data both to the developers, the contractor, when it comes to the detailing that's being implemented on site. So it has been common on a number of Part 3 projects. And then to your second question, yeah, there's very few data points, but one of the things I want to clarify is that window wall and curtain wall generally actually perform very well. It's that these project types are harder to achieve the air leakage target because of some of the complexities on site. So like I was mentioning, we want to temporarily seal all of the mechanical systems during the air tightness test or prior to the air tightness test so that we're not measuring air leakage through any vents or mechanical systems. But in a lot of cases, especially on high-rise towers, when you might have 20 stories of, let's say 10 suites on each floor and 20 stories, it's a lot of building prep to conduct. And in a lot of cases, you might not be able to access some of the vents from the outside. And so if you have any air leakage through the ducting itself, even if you seal the vents from the inside, if you have any air leakage through the ducting itself, it will unfortunately not be possible to seal those vents from the outside unless you're using maybe a swing stage or something like that. But we haven't seen that done. So window wall and curtain wall do actually generally perform very well. When it comes to air tightness, it's just the building archetype that has some complexities that make it difficult to achieve that air tightness target.
Great, and I think Nicholas had a follow-up to that. So
Sure.
for the question 2, the leakage is mostly coming through unsealed mechanical vents?
Yeah, correct. We've done a number of high-rise towers now where we are seeing either air leakage through unsealed vents, or like I was trying to say, even if they are sealed from the inside, we do often see air leakage through the duct itself. And if it's not sealed from the outside as well, then that air will leak through the duct and out through an exterior vent. So it's really complicated, really tricky to try and prep these buildings for air tightness testing, but that's kind of where we're at right now.
All right, that looks like all the questions we have for now. So does anybody else want to put their hand up or have any other questions for our presenters in the chat? You can feel free to post them.
Yeah, now that Kevin is away, I'll take over the closing notes. So yeah, I mean, like in the meantime, keep your questions coming. And we do have luckily, we are like 15 minutes earlier than expected. So now just give me a second. Okay, so firstly, I'd like to thank JRS team for this very informative session, and I'd like to say that we have already posted a survey link, and maybe Kira, if you could do that again, just in case. So please do the survey link, and this is how we do understand how we did, and what can be improved, and also the survey results really helps us to justify the resources we spend on hosting similar events. So please help us do the survey, and it also helps us shape the future events. A few other notes: this session will be recorded, and it's already recorded, and then it will be posted on our Green Buildings webpage and also Green Buildings on Demand learning portal. So share it with your peers and who could not attend today, so that they can earn credits as well. Now, most importantly, I would like to thank Kira once again for all her efforts in supporting the Building Energy Department, including hosting this event. If you get a chance to visit our Green Buildings on Demand webpage, that's actually a reflection of her work. So we did a lot over the last 8 months with her help, and we all collectively wish you all the best, Kira, for all your hard work and rest of your education and career goals. Thank you. So please do
Thank you.
please do the survey. Thanks a lot.